Module 4 Mastery Assignment by Leslie Oy. Topic 1. Particle Motion. There are three concepts we need to keep straight when we're dealing with particle motion. First, there is position, which determines the location of a particle at time t. Then there's velocity, which is the derivative of the position function. This determines how fast the position is changing at time t. The direction is also indicated by the sign. Then there is acceleration, which is the derivative of velocity, or the second derivative of position. This determines how fast the velocity is changing at time t. The sign indicates if velocity is increasing or decreasing. There are also several terms we need to keep straight. Initially means when t is equal to 0. At the origin means when position is equal to 0. At rest is when velocity is equal to 0. When velocity is negative, the particle is moving left or down, or if it's positive, it's moving right or up. Average velocity is using the slope formula, which is the change in position over change in time, or y2 minus y1 over x2 minus x1. Instantaneous velocity is velocity at a single moment. Positive acceleration is when velocity is increasing, and negative acceleration is when velocity is decreasing. When velocity changes signs, that means there is also a direction change. Speed is also another important concept of particle motion that is important. It is essentially this absolute value of velocity. It tells us how fast a particle is going without regards to direction. When speed is increasing, velocity and acceleration have the same signs, but when speed is decreasing, velocity and acceleration have opposite signs. Let's look at an example. The data in the table gives selected values for the velocity of a particle moving along the x-axis. The velocity is a differentiable function of time t. At time equals 0, is the particle moving to the right or to the left? Well, when we look at time equals 0, velocity is equal to -3. Since velocity is negative, the particle is moving left. Is there a time during the interval from 0 to 12 when the particle is at rest? Well, let's look back at the table. Notice from 0 to 2, the velocity is changing from -3 to +2. So this means yes. Because we were told the velocity function is differentiable, it is also continuous. So by the intermediate value theorem, since velocity goes from negative to positive, it must go through 0. And velocity equal to 0 means the particle is at rest. Lastly, we're going to use the data from our table to find an approximation of the first derivative of velocity at 10 and explain the meaning of the first derivative of velocity in terms of the motion of the particle. So we're going to need our table again. We can use these four values and plug it into the slope formula to approximate our first derivative of velocity at 10. And when we do this, we simplify to -1/2, and then our units will be meters over minutes squared. This is essentially the acceleration of the particle at t equals 10 minutes. Let's look at a different topic, vector-valued functions. These are functions with a domain subset of real numbers, while the range is a set of vectors. This can be denoted as the following, or we can use unit vectors, like this, and they're usually bolded to indicate they are vectors. There are three vectors we can have for particle motion. We have the position vector at any time t, the velocity vector at any time t, and don't forget x prime of t is essentially the rate at which the x-coordinate changes with respect to t, or the velocity of the particle in the horizontal direction, and y prime of t is essentially the rate at which the y-coordinate is changing with respect to t, or the velocity of the particle in the vertical direction. Lastly, we have the acceleration vector at any time t. It is important to know how to calculate the second derivative of y with respect to x. If the smooth curve c is given by the equations x equals f of t and y equals g of t, the slope of c at the point xy is given by the following. This can be interpreted as the slope of the tangent line, the slope of the path of the particle traveling along the curve c, or the rate of change of y with respect to x, and the second derivative is given by the following as well. This is essentially the rate of change of the slope of the curve c with respect to x. Here are the steps for calculating the second derivative of y with respect to x. First we need to calculate dy dt, then divide by dx dt provided that dx dt does not equal 0, then calculate the third derivative of dy dx with respect to t, and then finally divide again by dx dt provided that dx dt is not equal to 0. Here are two formulas that are helpful to fully understand particle motion. First one is the speed of the particle, or the magnitude, which is the length, of the velocity vector. The second formula is the length of the arc of the curve from t equals a to t equals b, or the distance traveled by the particle from t equals a to t equals b. So you might be wondering, how does this connect to parametric equations? Well, they're very similar, except mainly for the fact we would have vectors instead of points on a graph. Here's what that looks like. Now that we know these things, let's look at an example. At time t is equal to or greater than 0, a particle moving in the xy plane has a velocity vector given by v of t equal to 4e to the negative t, comma, sine of 1 plus the square root of t. What is the total distance the particle travels between t equals 1 and t equals 3? Remember, here is our formula for the total distance a particle travels. And remember, we were given the velocity vector, so we already have dx dt and dy dt. So our integral bounds will be from 1 to 3, and now we can plug it into our formula. Once we do this, we can put it into our calculator, and we will get 1.860602326. On the AP exam, we can round to 3 decimal places, so our final answer will be 1.861.